In the previous videos, I have just given you enough reasons to motivate you that why design verification is required as a separate field. I'm getting a lot of queries that, okay, so where does this design verification actually fits in the bigger ASIC design flow, and what exactly we are verifying. So I thought it's better to have a short video on front end versus back end in ASIC design. Then we'll have a separate video on verification flow in ASIC design, and then the two important aspects that we need to focus on, the yin yang of verification. So let's just start with the first part, front end versus back end ASIC design. So here's this diagram that I really want to explain over here. So I think have actually already explained it over here. We start with the design requirement specifications, okay, and then we design the microarchitecture for the system, and then after the microarchitecture is designed, there can be an optional step over here which is called a behavioral model. So might be we can build a cycle accurate C model of the whole system just to check the functionality really quickly, just to check whether this really meets the requirements or not. Once we are satisfied, this is an optional step, but we can have it. And then after the microarchitecture design, we go for the RTL design. Okay. So before we move from the RTL to the synthesis and the place and route, this whole part is actually the called front end design. Okay, so in the front end design, we have this RT microarchitecture design and RTL design, and on top of that, we actually verify. We do the functional verification here as well. Okay, so functional verification also constitutes front end design. Okay, so what do we mean by functional verification? So this is the core focus of design verification. So you verify whether the RTL has been designed as per the requirement specification or not. Okay, so this is the main goal of design verification. So you don't stop at RTL design, you keep verifying your design, but at the same time you move on towards the synthesis part as well. Okay, and then if there is some custom, if there is any custom part here, custom design, just go with the transistor level modeling directly, but typically you go from the RTL design to the synthesis, so you get a intermediate gate level model. Okay, so this is called generic tech netlist here, and then using the PDKs, basically you get the transistor level model. From the gate level netlist you get a transistor level model, and once we have the transistor level model, then you can really perform the equivalence checking. So there is another verification step over here. So typically you do in our case, let's say if it is a synopsis, you can do this using synopsis formality, and likewise you have cadence conformal as well. Okay, so this is something you perform equivalence checking using these tools, and then once you have the transistor level model, then what you do that you go on and do the place and route, so layout, and after the layout as well you do some kind of a checking that is called layout versus schematic checking. Okay, and after the layout, you to go for the mask, and during this whole process you are doing the analysis, the timing and power as well. So we don't want to go that because that is a separate topic in the physical design, but I just want to check, I just want to emphasize you that the functional verification is actually from the specification to the RTL. So just checking whether the RTL has been designed as per the specification or not. And then so this is the front end design. And the other thing from here onward, this is basically the back-end design. So physical design is also called the back-end design, and RTL plus the verification, that constitutes the front-end design. I hope I have make it clear to you now, and let's just move. So let's say within the physical design, front-end design, so we have design versus verification. So whatever you are designing, let's say whatever you are designing here, RTL design, this is the design part. This is only synthesizable in hardware. So this is actually hardware. Okay, and this is synthesizable, but the other part, the code that we will be writing for verification, so this is not synthesizable. Okay, so that's why we typically use high-level constructs like we will be using here like OOP concepts over here, and so those are really not synthesizable. Just to tell you, and I'm time and again actually re-emphasizing this thing as well, that why verification is important. So the design time is typically less compared to the verification time. Okay, so you can say that up to 70% of your effort, up to 70% of your effort go into verification. Okay, and 80% of the all written code is often in verification environment. 80% of all. And if you talk about the ratio and the requirements of the verification engineers, because of this the effort that is demanded, so you have 2 to 1 ratio. So for every 2 verification engineers, we have 1 RTL engineer. So this is just to let you know the importance of verification. So coming to the next topic, so how verification is generally done. Okay, so there are 2 ways to do the verification. So one is the simulation, which we will be actually more focusing on, is using some sort of a simulator, like we will be using Synopsys VCS for this one, but you can use Cadence Xcelium if you have a Cadence tools, or you can use Mentor QuestSystem as well. So you can use any sort of simulator. So basically what you are doing is you are actually through software you are modeling real design. This is what you are doing in simulation. So since you are modeling real design through software, so that's why it is 10 power 5 to 10 power 6 slower than your real design. Okay, so it's, but still you can do it. On the other hand, for large complex designs, so if you have more investment as well, you can buy an emulation platform as well. So these are specialized hardware to be configured like an SoC. Typically they contain FPGAs based system, and both Cadence they offer Palladium, and Synopsys they offer Zebu. These are the emulation platforms offered by these leading EDA companies, and this is really fast. So you can see that this 10 power 3 times slower than real design, but it is around 10 power 3 times faster than the simulation. Okay, I think let's just stop it from over here. I have just made it clear to you the front end and back end design part. So what actually constitutes the design verification and why it is important. So in the next video, we will talk about the verification flow.